Welcome to the AFM and Nanografting tutorial.
In this video, we will explore some specific applications of the atomic force microscope.
Over the past 20 years, various forms of scanning probe microscopy have revolutionized surface imaging on the micro and nanometer scale. Unlike traditional optical microscopes, these instruments extrapolate surface characteristics, such as topography, from the interaction of a small probe with an imaged surface. Advances in these technologies have allowed modern forms of scanning probe microscopy to achieve sub-nanometer resolution, more than 1,000 times the resolution limit of optical microscopes. Here, we will explain how one such instrument, known as the atomic force microscope, or AFM, may be used for both high-resolution imaging and precise surface manipulation.
During operation, the AFM probe, or tip, is brought within a few nanometers of the surface to be imaged. Within this regime, the principal force experienced by the tip follows the van der Waals potential. An interesting and critical characteristic of the van der Waals potential is that it is defined purely by tip surface separation. At larger separations, an attractive force exists between the tip and surface. As the tip is brought close to the surface, it begins to experience a repulsive contact force. AFM imaging scans may thus be categorized based on whether the probe is held at a distance within the repulsive or attractive van der Waals regime. These are known as contact and non-contact modes of operation, respectively.
The AFM probe consists of a fine tip placed on the free end of a mechanically driven oscillating cantilever. During non-contact mode operation, oscillations in the tip are monitored by reflecting a laser off the back of the cantilever to a 4-quadrant photodiode. Ultimately, a measurement of the van der Waals force, and thus the surface tip separation, can be performed by monitoring how these oscillations differ from free oscillation.
In contact mode operation, the tip is brought within the repulsive van der Waals regime. In order to maintain mechanical equilibrium at this separation, the tip must apply a force to the surface equal in magnitude to the van der Waals force. To do this, the cantilever must be deflected or bent, leading to a spring force as described by Hooke's law. As with non-contact operation, the deflection is monitored with a laser. In order to image in contact mode, a feedback loop adjusts the height of the tip in order to keep it at a constant deflection, and thus a constant tip surface separation. The resulting map of the tip height yields a topographic image of the surface.
While the AFM was designed principally for performing measurements on surfaces, the technology may also be used to manipulate surfaces. One such technique, known as nanografting, allows for the precise patterning of organic molecules and larger biopolymers onto a given surface. Here, we will explore one such technique that starts with a bare, atomically flat gold surface. The surface is then coated in a self-assembling monolayer of alkane thiols, a simple, straight chain hydrocarbon which covalently bonds to the gold surface via the sulfur head group. This process is simple and involves submerging the surface in an ethanolic alkane thiol solution for 24 hours, allowing the individual alkane thiols to self-assemble in a highly ordered array. This leaves the underlying gold surface chemically isolated from the surrounding solution. If, however, an AFM contact mode scan in ethanol is performed at high deflection, the tip surface force will be large enough to remove alkane thiols from the scanned region, causing them to diffuse into the surrounding ethanol. This is referred to as nanoshaving. Alternatively, if this is performed in an ethanolic solution of a different species of alkane thiol, high-force scanning is accompanied by a subsequent assembly of the new species of alkane thiol onto the exposed gold. This is known as nanografting. After a completed high-load scan, the surface may then be imaged at a low force to show the resulting pattern.
In a slightly more interesting example, this process may be used to pattern biopolymers, such as proteins, in well-defined locations on gold. Here, an initial nanoshaving step provides an exposed region on otherwise monolayer-coated gold. Dicysteine linkers provide thiol functional groups that covalently bond proteins onto this region in a highly ordered molecular array. Subsequent study of the protein's folding dynamics may be performed by applying precisely defined forces onto the protein patch. One last application of this technique involves patterning tracks of poly-D-lysine, or PDL, onto a gold surface. Here, the patterned PDL acts as a scaffold for directing axonal growth in neurons. As before, a desired pattern is nanoshaved onto monolayer-coated gold. PDL then aggregates preferentially onto the nanoshaved regions of gold via physisorption. As a result, neurons plated on these surfaces will then adhere and grow on the tracks of PDL.
These and many other novel techniques are possible due to the versatility and precision offered by the atomic force microscope.
For more information on AFM techniques, check the video description. Thanks for watching.